because we will go back into this area here, the composition, with the formation of gas inside the battery. So we may have some pressure built up in the battery, and so this, and also some problems because the pressure may open the battery. As soon as the battery opens, it gets in contact with air. We have some fire or explosions. So this SEI formation, which happens both at the anode and the cathode, is very critical. It must be understood very well to have a proper operation of the battery. This is the reason why I'm discussing this in such a detail. You see that by many studies that I don't report here, mostly by SEM visualization, macroscopic visualization, and also by IR, spectroscopical test, the nature of this SEI is now being clarified. Actually, it seems like that this SEI is formed by an organic part and inorganic part. Okay, the organic layer is formed by compounds such as lithium alkyl carbonate, this one, and lithium alkoxide, this one, both deriving from the reduction of EC. Remember, the EC is one component of our solvent. These compounds react with minor impurity, for instance, water, hydrofluoric acid, and with CO2 to call compounds like LAF, lithium carbonate, lithium oxide, peroxide, and lithium hydroxide. These constitute the inorganic layer here, that being porous is filled by the organic compound. So there is an connecting layer. So the lithium salt, which is present in a solution, will be also inserted here. So this gives the ionic conductivity. Actually, now you see that the reactions are a little bit complicated, and I have reported here some scheme. Now, if you have, for instance, a solvent formed by PC, propylene carbonate, and ethylene carbonate, sometime here you can have propylene carbonate, then these are the scheme of the reaction. I don't go too much into the details, but you see that here we have formation of lithium carbonate, which is part of the film, and some polymer stuff. And if instead we have some linear carbonate, we have this kind of film. So it's very complicated chemistry. And also, of course, the salts which are present in the electrolyte can be decomposed. You see that all this decomposition reaction involves electrons. So when you have a passivation layer, which is non-permeable to electrons, this reaction stops. And you see that here we have many possibilities. The most maybe interesting for you case is this one of lithium hexafluorophosphide, which is the most common salt used into these batteries. And you see that the composition can give rise to some fluoride materials. And if you have some water, this becomes HF, which is very corrosive. Okay, we had to go another 15 minutes. So let's see now how a typical charge-discharge curve in the case of graphite develops. So this is the voltage versus lithium. Remember that the graphite is now tested in a semicell using lithium as a counter electrode. And let's see the fast discharge, which is the blue one. You see that we have some peak here with the composition of the electrolyte, and then these are all the stages, okay? And this corresponds to this process. Okay? All right, and this process gives oh no, sorry, the fast discharge is the red one. And in fact, you see at 0.8, this plateau, due to the composition of the electrolyte. And then we have all these plateaus, and at the end, we have a capacity of 420 something, right? 25 milliampere hour per gram. Remember, the capacity tells you the amount of charge that is passed to the cell. However, we know that the theoretical capacity, which is the maximum possible, is 370 milliampere hour per gram. So how is possible that experimentally we have a higher value? Actually, what maybe happen here, that this higher value is due not only to the electrochemical reaction, but something else which apparently gives a higher capacity. And this something else is the capacity necessary for the charge necessary for the decompose the electrolyte. In fact, when we go back and charge again the electrode, namely we go to this process now, we see that the capacity is going to the right value, namely 370. So this is capacity 1, capacity in discharge, capacity in charge is 370. When we discharge again, we go back here for the second time, we obtain 370. So you see, in these cycles, we have lost some capacity, which is so-called the irreversible capacity. And this, and here is indicated here, the reversible capacity that we obtain is 370. The irreversible capacity is the difference between a fast discharge and a fast charge, which is, of course, irreversible because it's due to the charge necessary to drive these reactions, which are the decomposition of the electrolyte. And this, of course, is some irreversible process. So we have to take into account that in this particular case, and in all the cases where we'll have some film formation, the composition of the electrolyte, and so forth, we have some irreversible capacity, which, of course, is not good for application, but we have to deal with it. Here again, you see that some model for the formation of electrolyte interface. And here we have two cases. One for which happens in solution using ethylene carbonate-based solution. And here what happens in a solution using propylene carbonate. You see that in these symbols, this represent the naked lithium ion. These represent the solvent molecules In the case of EC, of course, are EC molecule, and this represents the solvated lithium ion, which is the line with all the solvation. So in the case of ethylene carbonate, what will happen? That we will have the lithium ion arriving at these layers with the solvation, and possibly is inserted with solvation. You see, as I showed you before, that the solvated ion is larger than the distance between the layer. So if lithium enters in the solvation form, there is a deformation of the layers here. However, then what will happen is that the lithium may lose the solvation, and we have just a blister. Or more simply, what will happen here, that the lithium ion will lose the solvation molecule as enter as a lithium, naked lithium. However, in the case of propylene carbonate solution, we don't have this possibility of desolvation, because the solvation of a lithium with propylene carbonate is much stronger than that with ethylene carbonate. So lithium enters as a solvated molecules, and what will happen, that this will destroy the graphite with exfoliation. So this is a bad effect. And in fact, this is shown here. Okay, after this, we'll pretty soon finish. You see that this is now the voltage profile of graphite in ethylene-based solution, which is this one. And we see that here we have the same reversible process that I showed you before. Because in the case of ethylene, we have first here the decomposition of the electrolyte, which gives us the reversible capacity. But then after that, we have insertion into graphite in a reversible way. Instead, in the case of propylene carbonate-based solution, you will see that the voltage will eat the decomposition of the electrolyte, approximately 0.8, but it will never recover. I mean, what will happen here that we will never have insertion of lithium into graphite, but a continuous decomposition of the electrolyte. So it's not a good idea to use propylene carbonate-based solution with a graphite electrode. Okay, I think that we may stop here, because now we will go into some other materials, and I think that I already gave you a lot of information, and you may be a bit tired. So, thank you very much.